So this is joint work with Christos Dimilos and Stephen Chon from Harvard University. So writing an application usually involves incorporating frameworks and libraries, but there's also an increasing trend to use internet-connected services as well. For example, an application might want to leverage Twitter or other internet-based functionality in their application. But it's not just client-side applications that follow this pattern. Those back-end services that clients communicate with are also internally implemented like this too. And they're actually quite complicated internally. To get a sense of just how complicated, look at a question that came by that was asking, how complicated is your system? To which the Amazon CTO responded, well, here's a picture. And here, every node is a service, and you can ignore the coloring of the nodes. And every line is an interaction between the two connected services happening at runtime. So what's enabled this massive style of applications? Well, the answer is a relatively new paradigm called microservices. And that's what I'm going to talk about today. So in particular, I'm going to present WIP, which is a contract system that helps developers put together these microservices. So first, let me explain what microservices are in more detail and why developers need help. So to understand these problems, let's see how one might use microservices in their application. So to that end, I'll focus on a popular note-taking service called Evernote and how a client program accesses a notebook that was shared with the user through the Evernote API. So each user's notes and notebooks are stored in a distributed database called a note store in Evernote. Users can access notebooks with them through what Evernote calls a linked notebook. So accessing a linked notebook may require contacting a different note store than the one the user contacts for their own notes. So let's see how that works. So to access a shared notebook, a client uses this list link notebooks operation. They then receive a share key and a URL for a service that contains the shared notebook. The client then contacts the server at the note store URL and authenticates to the shared notebook using the share key provided though. They then receive a new auth token to use in the subsequent requests. And then finally, they can access the shared notebook by calling a find notes operation, for example, passing one of the arguments, that auth token that they received before. And then, only then, they get the notes that they were after. So how did a program know how to do all of that? Well, the documentation basically. And here's a snippet from the developer documentation for the find notes operation. And so there's lots of properties in there, and so here are two that I just pulled out. Documentation gives this requirement that the offset provided must be non-negative. Another one is that the return note list is less than or equal to the max notes parameter. Okay, but there are other more complicated invariants encoded in this documentation as well. So here in the documentation for list link notebooks, it states that the note store URL return is just a URL that clients should use to connect to, and additionally, they can access the shared notebook by using that share key also returned in list link notebooks. And the network protocols themselves, the actual programmatic interfaces for these services, aren't much help for figuring out how to use this service. So here's a snippet of the actual network specification for the Evernote API, given in Thrift IDL. So what the note store URL is just encoded as a simple string. So developers need to heavily rely on the developer documentation to understand what they should do with that string and how it should be interpreted. And unfortunately, though, developers make mistakes. So to make matters worse, these low-level network protocols aren't much help either. Did I get anyone? So they can't express and check the properties that these kind of applications use, which can make it easy to misuse a component's interface or fail to implement it correctly. For example, here's a user asking for help using this API because they're getting this not very descriptive permission denied exception. To debug it on the forums, they had to go through their entire workflow describing what they did. And there's actually many forum posts on the developer website and on places like Stack Overflow asking for help on just this particular flow I described, which is really just one small part of the overall API that just Evernote provides. And it's not just Amazon or Evernote that writes applications using these kinds of network protocols either. These simple network protocols force developers to inject brittle defensive checks in their code. And if they miss a check, the results can be catastrophic, especially when the size of the application grows. For example, Amazon faced issues by not validating interactions between services, and that caused widespread internal outages. So with that in mind, it's It's interesting to note what the community calls these kinds of diagrams. They call them the Death Star topology. And Death Star is actually quite apt for these microservices, I think, because if you think about their fragility and the fragility of the Death Star, remember that in Star Wars, a single component failure led to the whole Death Star blowing up, right? And so there's kind of a clip of it. So that's microservices. So the most important point I want you to take away from microservices is that using these simple network protocols leads to a loss of abstraction. And that loss of abstraction leads to brittle serialization techniques. But almost paradoxically, these simple network protocols are a feature, not a bug, of microservices. They really are at the heart of it's what enabled companies to write these large-scale applications. So like it or not, the simple network protocols are here to stay, and we have to deal with them. So how do we deal with the loss of abstraction arising from these simple network protocols? Well, there are many approaches to establishing and enforcing abstractions, which we all know about and love to research. For example, there's session types, distributed object protocols, distributed runtime monitoring systems, just to name a few. But the microservices paradigm has a lot of unique challenges not adequately addressed by that work. The first major hurdle is that microservices embrace independent deployability and updatability. So we can't assume a global deployment for any kind of solution we come up with. The next hurdle is that components are written in a multitude of programming languages. This benefit actually arose from using these simple network protocols because the interfaces didn't rely on any particular programming language features. And we shouldn't try to reinvent a more complicated network protocol in the end, like Corba or DCOM, or one of those enterprise service buses even. They were avoided on purpose due to their pragmatic shortcomings, so we should learn from that. And finally, and related to the previous point, is that we need to deal with the fact that there are no single network protocols used in these applications. Those decisions, like almost all decisions in microservices, are made in a very decentralized way. Every service owner gets full control over what they're doing with their implementation. So to address this problem, given our challenges, we developed WIP. WIP associates each service with a service contract. It's a precise and enforceable specification of the expectations of and promises to other services. WIP service contracts embed predicates written in a full-fledged programming language inside a domain-specific contract language. WIP checks these service contracts when the service is run by transparently intercepting the messages that they send and receive. So now I'm going to give you a taste of how WIP works through our Evernote example. So let's take a look at how we can encode some of the informal properties of the Evernote workflow into an enforceable WIP specification. The first kind of properties we look at are just first-order predicates that I mentioned before. So here's the WIP contract for the first-order properties. The requires predicate specifies that the offset is provided greater than or equal to 0, and the post condition uses the max notes argument to check that it's less than or equal to the resulting list size. So note that WIP doesn't include type annotations in the contract, as the underlying network specifications already handle that. Instead, we only focus on bridging the gap. The predicates themselves are written in Python, which is mostly an arbitrary decision. We don't really rely on any Python-specific features inside the contract. But so you could imagine contracts being written in any of your favorite languages. So let's move on to a more complicated properties of the workflow that I mentioned before about contacting a store based on a URL return. We'll be capturing that the node store URL return will be used to contact another node store, and moreover, that the appropriate share key is used. So first, to capture that the return node store URL implements the node store contract, WIP operation contracts can identify other service contracts from their messages. This snippet specifies that the node store URL return will satisfy the node store WIP contract. And then the for each states that we'll enumerate over the result list, and that each item in the result list will identify a WIP contract. The identifies keyword states that the node store URL value in the notebook refers to another node store service. But unfortunately, though, like I alluded to, this isn't quite enough. In practice, operations also tend to pass around possibly an updated environment from one call to the next, and possibly between services too. If you want to think about this in a more familiar way for ICFP, you can imagine the services are trying to pass around a closure, but are restricted from doing so due to these really simple network protocols. To see an example of this, I've highlighted a flow of tokens that we're interested in here. And to reuse the closure metaphor, the tokens here are acting like the environments, and the endpoints you're contacting are like the function pointers. So in WIP, we use contracts to capture these kinds of higher order properties. The parameter, or what I'll call the index, is used to differentiate between different instances of the service by using the environment as the index, specified as one of the arguments. So here's the updated contract. In the first line, we included K, the index to the contract. That K index can be specified in where conditions in the operation contracts. So for example, in the find notes operation, that refers to the auth token. And additionally, in higher order operation contracts below, it can specify the index for the service contract you're identifying. So here it's the share key given in the resulting linked notebook. So let's see how WIP can enforce this contract. The adapter maintains an internal state that associates an endpoint with that contract. At this point, the adapter is just configured to associate the Evernote server endpoint with the NoteStore contract. So WIP learns of new services by intercepting the messages. It updates an internal state to associate every endpoint it received with its contract. This is all done automatically according to the contract. But remember that WIP is transparent to the services it enhances. So the client sends and receives the same messages whether WIP was there or not. The service doesn't know about WIP. In this part of the communication, when the client is performing the authenticate to shared notebook operation, the NoteStore contract with index share key is used, and that identifies another index contract with index auth token. So this captures the exchange of tokens. The at receiver syntax here just means that it's at the same endpoint. So now what happens when there's a contract failure? Well, WIP will blame the party responsible for the contract violation. So in this example, if server 2 provides more notes than requested, WIP would blame whoever is recorded was the source for asserting that server 2 would uphold that contract. So it won't necessarily blame server 2, even though it's just sent this violating message. That could be because server 2 doesn't actually implement the NoteStore contract, and that Evernote server accidentally just gave the wrong endpoint. So actually, in this case, Evernote is blamed. And intuitively, to kind of bring back to this functional programming style, you can think of the server being identified as being part of Evernote server's return value. And since it vouched to implement the NoteStore service, part of that vouching also meant that any of the services it originally identifies in its results in the list link notebooks operation should also satisfy the NoteStore contract. So far, I've only talked about one client talking to services that don't know anything about WIP, and it works. Partial deployment works. That was what we set out for. But if we know that other components are WIP enhanced, we can do better. So to make blame more precise, when the destination is also deployed with WIP, an adapter adds extra information to help the receiver adapter improve the accuracy of its blame information. So in this example, the Evernote server can send a precise blame level of how Evernote server learned of server 2. But from the perspective of the services, this is totally transparent yet again. The message is enhanced only between the WIP adapters. Also, we don't add any new messages, we're just piggybacking on the existing ones. So the upshot of this enhanced communication is that when a client encounters an error, it can now more precisely identify that Evernote server 2 was the source of the fault. Also, this lets the Evernote server avoid being blamed for services it just learned about. So you might imagine a scenario, possibly, where partner organizations may want to work with Evernote, and Evernote might not want to take responsibility for servers that it's working with that it doesn't control. So here, maybe OneNote is also satisfying this contract. So now in the last part of the talk, I'm going to switch gears to claim that WIP really does work. So we evaluated it in 3 ways. Theory, to make sure the design was sane. We also applied WIP to 3 real-world case studies that we think are representative of many popular microservices. And then finally, we evaluated the performance overhead to make sure it was usable. So we formalized WIP focusing on propagation of blame information. So we show that blame information pinpoints the services whose code is the source of the deviation from the contract. So to show this, we reason about what happens when a contract error is logged. So when WIP logs a precondition error, then WIP blames the label of the sender of the request message, as the error in using the service must have come from that party. But the more interesting case is when WIP logs a post-condition error. Then WIP blames only the entities that the violating service satisfy that contract. So in WIP, blame is essentially the summary, a summary of the provenance of a service's name used in a context that binds it to that contract. So provenance of a service in this setting is in general a global distributed property of the application, but the blame information, which is local to the WIP adapters, that provides a sound summary of distributed provenance information. So you can see the paper for more details in the precise formalism. So in addition to formalizing the key properties of WIP, we also implemented a prototype. And to solve the challenge of dealing with multiple protocols, we have a network plugin system that allows WIP to use REST, Thrift, and SOAP. And others can write their own plugins for their favorite protocols too. So we also evaluated its practicality on 3 case studies. We looked at the Twitter REST API, and also we found a bug in one of the clients for a popular correspondence chess service. And the bug there was we weren't able, they basically had a documentation and their implementation didn't match it, and WIP caught it. So all the contracts were stated informally in the documentation, and then we precisely enforced them using WIP. So we also evaluated the performance of the prototype implementation on 3 case studies and reported on its overhead. So the baseline for these charts is 0. So if all the points were at 0, that meant WIP added no overhead. So the chart on the left is network latency overhead. So since WIP intercepts and checks each message a service sends or receives, it adds about a 20 to 80 millisecond overhead for each message. So for the case studies, this was actually within their SLAs, their sort of informal SLAs for their APIs. So we felt that was pretty acceptable for their case studies. For example, the Twitter REST API tends to have on average about a 500 millisecond delay. So the middle chart is the memory footprint overhead. So since WIP needs to keep internal state for which endpoints it's monitoring and their corresponding blame labels, WIP keeps a file-backed database where recently used services are held in memory. WIP's in-process memory footprint, it stays constant, while the disk-backed store does increase as you identify more new services. And then finally, an enhanced communication between 2 WIP adapters. WIP includes additional information in the messages, such as the blame labels used for any services identified. This overhead amounted in about 25 to 125 bytes per enhanced message on average in our case studies. So to sum up, I just want to say that WIP aims to reestablish the useful abstractions to programmers in this new microservices paradigm while adhering to the strong pragmatic constraints of that paradigm. And you can find out more if you go to whip.services, and you can even play around with WIP in your browser without installing anything. So thank you.